All right, everyone. This is Mr. Lee. This is our kinetic energy post lab. This is the first lab of this unit, and the first lab of the semester, and we are getting more and more geared into the AP world. And so hopefully this video helps us out. So, without further ado, let's begin. All right. One of the first things that I want to go over is the calculation at the beginning that I gave you. I gave you the idea of the initial energy. Okay. And the idea of the initial energy, I told you to multiply the object's mass, okay, times 9.8, okay, and whatever the height was. Now, this is actually a formula that we use in physics, and it's called potential energy, right? So U and lowercase g. And I'll go over what each of those variables mean in a couple of seconds. But for the official formula, UG is equal to M, and then 9.8, of course, is G, and we have H. All right. So the U, it stands for potential. Now, you might be wondering, Mr. Lee, why don't we use P for potential? And the reason is we use P for another variable. Well, there's two variables that we use. There's the capital P for power and lowercase p for momentum. Um, Only power starts with a P, and momentum doesn't. And potential also doesn't start with P, but that's the world we live in. And that lowercase g is what we call the gravitational potential energy. Now, the gravitational potential energy, we're going to go more into it with further notes. But just so you know, the formula that I gave you at the beginning is actually the formula for gravitational potential energy. But we did call it our initial energy. So just keep that in mind. All right. Now, when you graphed this initial energy, I just told you to call it E, right, for initial energy, and you were supposed to graph that with V for velocity, right? And if we take a look at the units here for E, we can do a couple of unit stuff in a little bit, but let's have that down so that you have it for future. The units for M is kilograms. The units for G is meters per second squared. Okay, and the units for height is M for meters, and so that does clean up into kilograms meters squared per second squared, and this is our units for energy. Now, that is a handful and a mouthful, and it's a lot to write. And this actually does, we have a different variable for this unit, and I'll get that to you at the very end, or maybe even the next video, depending on where this video goes. All right, so if you did this lab correctly, and as you change the heights, you change the different kinds of energy. So I'll write that here. We changed our heights. So we had different uh, energy to start. And if you got some good data and you and your lab partners were able to time it effectively, you should have gotten something that looked like this. Right now, if you have a graph that looks like this, and this is good practice for future AP style questions in case they ask you to linearize, we need to be able to linearize this graph. So this right here is a exponential graph where if we had to linearize it, so let's do this. If we had to linearize this graph, we had to linearize the denominator. And if you plug that into your Google Sheets and you mess around with it, hopefully you got a linearized graph that had you square the velocity in the denominator and would have given you something linear that looked like this. All right, so here's the cool parts, right? So with this, you'll also have gotten a slope, okay, of some value. Now, hopefully, if you take a look at the slope, one thing that I hope you realize is that once again, in physics, our numbers actually mean something, and this slope if you were a shrewd detective, you would have noticed that the slope was equal to a half of our mass, okay, whatever that number was. And so at this moment, we can actually come up with our generalized formula. We can say that our initial energy or initial kinetic energy is equal to the slope times v squared, right? So I'm going to actually take a step back and show you where I got this in terms of the linear formula, right? And so the E initial is our y-axis is equal to the slope, which is m, and our x-axis was v squared, so mx plus b, right? And our y-intercept, our b in this case was going to be is 0, because if you release the object from a height of 0, right? So a height of 0 gives you a velocity of 0, and so we can say our initial data point of 0. It does make sense in this sense, so I'll put it right there. And so what we get here is that our y-axis is the initial energy, okay? And let's make this a little bit thicker. There we go. Our slope, that was this number that we got right there, and that x-axis is our v squared. Okay, and so with here, if we link with what I just told you earlier, we see that the energy or kinetic energy is equal to 1/2 times the mass. Okay, now just so you know, let's put a little star right here. This mass is mass, right? Or this m is mass here, and this m up here in this formula, that m means slope, right? So you got to make a distinction. Right? 1/2 mv squared. Now, this is the first of many formulas that we're going to derive for this unit. This formula right here is called the kinetic energy formula. Okay, and with this lab, you're able to actually find the kinetic energy formula. Now, I want to go back to the units, okay, that we had for energy and see, you know, what that all translates into. So if you take a look, we know, so the 1/2 doesn't have any units, and so I wrote that in, but I'm just going to cancel that out. The units for m is kilograms, and velocity is meters per second. But if we do meters per second times meters per second, right, because our velocity is squared, we get kilograms meters squared times second squared, which is the units that we started off with earlier, right, up here. And we got that because I told you to multiply the mass of your object times 9.8 times the height. Now, this is really cool, right? And so this kilograms meters squared per second squared, we got it from the m times g times h formula. And lo and behold, the kinetic energy formula down here has the same units. And so with this jump to conclusion, we can say that the gravitational potential energy units and the kinetic energy units, they all have the same units. And so the units for energy, okay, no matter if it's gravitational potential, if it's kinetic energy. Oh, by the way, kinetic energy, we don't usually write it as E subscript K. We write it as KE for kinetic energy. And we're going to come across another type of energy called spring potential energy. So potential means is U, and spring is for lowercase s, right? Or any type of energy, we call that a joule. Okay, and that's a, let's see, Joule. It's a capital J, and we physicists use the capital J instead of writing kg m squared over s squared. All right, and that is that. I think the other important thing about this here is that we can make a couple of big jumps and big distinctions, right? So we know that our graph look like this, and it also look like this, right? So we can say that the initial energy, right? And in this, I'm going to put in parentheses, UG is directly proportional to V squared. Now, for us to get ready for the FRQs, we can say that this initial kinetic energy is directly proportional to V squared, like so. All right, but based off of our most recent discussion, where we talked about how the initial potential energy is the initial energy that I told you to talk about, we can also say the same thing, right? We can also say that for this lab at least, our UG was directly proportional to our kinetic energy. Okay, so it was a 1-to-1 ratio if you take a look at this graph over here. Yeah, so with this, we're going to go into this a little bit more later on because this here is one of the biggest formulas for, I don't know, mankind. It governs the universe, and it actually helped physicists think of many crazy ideas. Something like dark energy comes from this idea right here. All right. So this one is huge. So look forward to that video in the future. All right. I'll see you later. Bye bye.